my name is Darren Khoo. I'm the solution architect at Topan Aquarium. So my job is really to combine all the requirements from the business, functional, and technical requirements, and I roll them into sushi, and join them with a cup. That's my job. If I do my job well, everyone is going to have a good time for the next 5 years. If I do a bad job, what's going to happen is that next 5 years, everyone is going to curse and swear at the system because it's breaking down and all these things. So that's really my job. So having heard about cloud native from CK, about the different properties of the cloud native application, and now I'm going to show you how actually a real world case study about how we actually built one the cloud native way to serve a project that has a very high performance requirement. So this is nothing beats hearing a real case study. So this is a real project that we have implemented, that we have rolled out, and it's already commissioned. And due to the confidentiality of this project, I cannot share the exact details, so I generalize some of the concepts. But they are pretty much still the key requirements are there. So later, if you happen to know about what this project is all about, please keep it yourself and don't ask me trick questions after the session. Okay, so basically, before we got involved, this particular agency actually has a system that they actually deploy in the form of a mobile device that they have to deploy this to more than 1,000 locations, and it's meant for some event registration. So what they did is that they deployed a solution that runs in a mobile device without any connectivity. So what it really means is that they have to load the database into the device itself, and they have to deploy to 1,000 locations, and they have to make sure that the right data gets to the right device and goes to the right location. So you can imagine the amount of logistics involved just to set up this thing. So there are some challenges that they face. Obviously, there's no network connection, so data distribution is a nightmare. And it's very difficult to collect the data at the end of the day because they are all on each individual device. How are we going to combine them back together again essentially? So that is a very big problem itself. And during the course of the event, there's no way for them to report the progress of the registration and all this. How many participants come out, turn up, and each time of the day, and nothing. And they have to manually report. So each of these 1,000 locations have to manually send an email, send a WhatsApp or whatever back to the agency. And somebody has to manually report. So you can imagine this is not ideal for this kind of the scale of deployment. So they decided to throw a tender with a new requirement. And because of due to the confidentiality of this project, they decided that they're going to deploy on GPC. Then that was the original thinking. And these are the key requirements. Again, it's across 1,000 global locations. And but the difference is that this time they are hosting a central system. So this 1,000 locations is going to connect back to the central system. So which means that now the pressure is now on the system itself. That means you got to support all these 1,000 locations, and there are over 4,000 concurrent users because every location they are going to deploy a few terminals. So it ends up to about 4,000 plus concurrent users. So for those who have built system before, you know that 4,000 concurrent users is in Singapore context at least, it's a very high number. So typical system that we roll out is 100, 200, or maximum 300 concurrent users. But this is 4,000. And because of the criticality of this system, it's mission critical, so they have a very high requirement, 99.95. To give you an idea, so a typical government license system is 99.5. And if you calculate it mathematically, in 1 month, there's an acceptable downtime of roughly 3.6 hours. So with 99.95, What do you guess is this number? Anyone can have a sense. Want to try guessing what is the downtime acceptable for 99.95 system in 1 month? So I calculated mathematically this morning. So it's 21 minutes of acceptable downtime. So it's very stringent. And this 21 minutes is provided as a 24/7 system. And this system is actually not 24/7. Yeah, so it actually cuts down even further, maybe just 10 minutes in acceptable downtime. And although it's a very high concurrent requirement, they also need it to be fast. So it's 3 seconds, 5 seconds for 90 and 95%. This I think this is quite typical, except that most of our system they don't have such a huge concurrency. And it's going to serve 2 million over participants in a single day. So they actually specify a peak throughput of more than 1 million registration in 1 hour. So that is what they expect when everyone comes at the same time. So a lot of systems don't have this specification, but this particular one has. And they were thinking that because it's so mission critical, they're going to build another DR site. Because GPC 1 has 1 and 2, so their plan was to build a DR site. Therefore, they have some RTO kind of specification. And lastly, they want visibility, because they are lesser than the previous system. They have no visibility at all what's going on in the ground. So they added this as a requirement. So visibility in terms of system health and registration status. So everything must be immediately available and be able to look at the latest aspects. So with all this requirement, it's a huge challenge. We took on this project, and I'm going to share what we actually did. Okay, so before that, the agency was actually looking at all this requirement, this solution in the following way. So I summarized what you saw in the previous slide into 4 key requirements: high availability, high performance, resilience, and stability. So they were looking at a very traditional way of doing things. So high availability, I just need to make sure I have redundancy instead of 1 I server at 2. So that's serve the high availability. That's a very traditional way of doing it. High performance, I just increase my CPU memory. The database, I can just do vertical scaling to serve high concurrency. So that's what they thought. And to meet this high resiliency, just have a main and a disaster DR site across GPC 1 and 2, active, passive. Anytime you can just pay over to the hot standby. So yeah, that's the other thing. High visibility, I just pipe all the logs into a central log, and all the parameters, all the monitoring and all this, I have visibility. That's what they specify in the specs. So, but of course, this very traditional approach may not be able to serve such a high requirement based on my experience. So there are certain downsides. I'm going to just share a few. So you keep increasing CPU, VM resources. It's just going to increase your cost exponentially, and you may not be able to solve the concurrency issue as well. And especially at the database, at this kind of concurrency, the database, based on my experience, is going to be the bottleneck. So if you scale a database, you can only scale vertically, and you will hit a limit somewhere. Even if you can give you all the CPU, you also cannot. With traditional database technology, when the concurrency starts to build up, give you all the CPU, you cannot even solve it. It's very difficult to scale when the database hit the bottleneck. So to meet their RTO, if you remember seeing the number, RTO is 50 minutes, RPO is near 0. So you need a very high network throughput. And guess what? GPC has limitations. Max child CPU, the bandwidth within site is only 300 megs. Maximum, if you subscribe for the maximum, this is a maximum you can go. So everywhere we are seeing bottlenecks. So when we bid for this project, we actually try to propose a different, more cognitive approach. So we apply all this principle. So Today I'm going to share how we actually so-called come up with something that is able to meet all this performance, and we really met the performance and we really launched the system in a very short time. So our approach is that we took a very different way. So firstly, we convinced the agency to go to the cloud. Yeah, so there's this GCC 2.0. It was just recently launched, I think last year. So we actually took some risks and we pitched to the agency that we should go GCC 2.0. So they somehow, yeah. And then we will apply this N+1 redundancy. Later I'll explain more on that. And to meet a high performance, we're going to go microservices. Actually, the tender didn't specify for microservices, but we actually proposed that. And to go even further, we actually say that we're going to use an event streaming architecture. So probably there's something you guys haven't heard about. Later we will share more on that. And to meet a high resiliency, instead of having a primary and DR side, we're going to maximize across 3 AZs in the cloud. So I will explain more on that as well. And for high visibility, we don't just do monitoring, we do observability. So the difference, maybe the slight difference between observability and monitoring is that monitoring, you're just monitoring the surface. For example, whether you have fever, you have flu, all these surface things, blood pressure, all these things. But observability is actually going right into inserting probes into your internal organs and testing everything that can probe. It is like you can't do that with human. You cannot insert probes in your body all the time. But with a system, you actually can do that. Okay, so now we have convinced the agency to go to the cloud. So how are we able to maximize the cloud infrastructure to achieve maximum availability and resilience? So I'm going to explain why conventional HA that we have been so familiar with is actually not good enough. Its problems, and why we propose to go 3 AZ. There's a reason why the number is 3. Later you will see. And with this, how we actually maximize and achieve the high resiliency that we need for this project. Okay, firstly, conventional HA, if you understand how it works, this is actually very simple. So you have two nodes. One is acting as primary, one is the passive secondary. So if you have data that you need to sync across, the primary will actually sync across to the passive. And typically the passive node will have this is just a simplified way of how it works. So you will send a heartbeat to the primary, and if you receive a response, you will know that the primary is built up, and then it will stay as a secondary. So that's typically how conventional HA works. But the problem is when there's a breakage in the network, or when something goes on in the infrastructure, then you have a problem. So as a solution architect, I will tell you the bad news that if you design a system assuming that the network is reliable, the net bandwidth are unlimited, I mean, you've heard this before, you're going to design for failure. So with this conventional HA, it doesn't actually tolerate when there's network failure. Because what happens is that both will think they are primary. Because I can't see, the secondary can't see the primary, and I will think that the primary is down, I'm going to make myself the primary. But the primary is thought that I'm the primary. So that's what happened. So essentially you get a split plane scenario. So a split plane is where both nodes think, each of them think I'm the primary. So I'm the master now. So I take over. So, but then we all also know that the split plane is going to cause a lot of problems. So you now have unexpected behavior. For example, you use a reddish cache, and now they are both thinking they are primary. So your session may go haywire and all that. And typically, it causes data inconsistency, and it's very, very difficult to recover. Yeah. So that is the situation that we need to avoid. So what modern software or in the cloud era, how software actually do clustering is based on a very different approach. So it's called a quorum-based consensus approach. So with this approach, it actually requires a minimum of 3 nodes. So I roughly explain how it works. Of course, I'm not getting into the technical details, but so you have 3 nodes. One node is the leader, the rest are the follower. So again, all these principles still apply. So you have data sync, you have heartbeat and all this. But the only difference is that when there's a network partition or when the leader goes down, so what is going to happen is that the remaining healthy nodes is going to re-elect new leader. So they don't just assume their primary when they discover the primary node is down. So they will do a sort of like a election. So they will then appoint a new leader. Because the way the algorithm works is that you need a majority, you need a quorum. Quorum means that you can form a majority to elect a leader. That will mean that no matter how you partition your network, you're never going to get into the sweeping scenario. Because if let's say this leader is now isolated on its own, and these two actually form another partition. So this leader will immediately cannot be the leader because there's only one, there's no consensus. And these two passive nodes, because the two of them can form a quorum, because 3 out of 3, 2 is majority. So they can re-elect a new leader here, which is what you see here. So there's never going to be a split scenario. In the worst case scenario, that all the 3 nodes all get partitioned, so you will end up with no leader, your cluster goes down. So you will never have a split. There's no chance for that to happen. So remember, modern software uses this 3 node cluster in the cloud era. This is what happened to all the for example, your Redis, your MongoDB, your even SQL Server AOAG is actually based on this kind of clustering. So you have primary, secondary, you have to witness this acting as to form a 3 node quorum. So actually, you have 3 node cluster, you can tolerate 1 node down. So just remember this, because the 2 remaining can form a quorum. If you have 2 nodes down, sorry, your cluster is down, even though you have 1 node that is healthy. So that's how it works. That is essentially to prevent this kind of undesirable situation where there's a split rate. So with this understanding, how are you going to deploy your cluster? So I think you guys have heard about this event, hopefully not for the wrong reason. I hope your system are not affected. So this actually happened in February this year. So Azure actually has an outage. So what happened was that there was a power surge, and it causes some of their 5 or 6 of their cooling units to actually shut down. And they couldn't get it up. They couldn't get the cooling unit up because of some other reasons. And they end up having to shut down part of all the compute. Because when the data center gets heat up, the hardware will start to down. So dealing with themselves, they don't have a choice. They actually shut down a lot of the compute resources, and that results in the equivalent of what whole AZ goes out. So don't think that the cloud is always there, it's reliable and all that. The cloud can go down and one whole AZ can go down, and it has happened before in this instance, and this is not the only time it happened. If you go back to the past history, Azure, all the 3 clouds, they all happened before. So the fact is that the whole AZ can go down. So which brings us to the question of why I say 3 AZ. There's a reason why the 3 CSP has actually deployed 3 AZ in Singapore. The number 3 is not by chance. It's essentially because they know that this is how modern software do clustering. So it comes in 3. So if you think that 1 AZ cannot go down, cannot happen, right? So you deploy, a lot of agencies I've seen or heard, they actually use 2 AZ. They think that having 2 AZ good enough, because I one down, the other one is still up. But because of the understanding of how this new modern software actually do clustering, you'll find that now AZ2 become your single point failure. If AZ2 goes down, your 2 nodes go down, you're left with 1 node. Even though it's healthy, it's going to come down. For the reasons I explained earlier. 1 node cannot form a quorum, so So there's no way for the one node to index itself as a leader. It doesn't work. So the correct way to deploy this is that you deploy them across 3 AZ. So there's no single point failure. So any one of this AZ can go down and your cluster still survive. So that's why we designed the system. We convince them we got to go through 3 AZ. Yeah, just to maximize the cloud. Okay, so I'm going to cover next about how we actually meet the high performance requirement. So I will repeat some of the key requirements here so that you are aware. So there are 4,000 world devices registering concurrently. And then there's more than 2 million participants in a single day. The peak throughput, if you work out mathematically, is actually about 400 registration per second. At the peak. So there are some business logic that we need to implement. Key one, I'm not going to, there's a lot of detail if you want, but I'm just going to give you a few key requirements. So they can only be registered at the assigned location. Why? Because crowd control. So if you don't have this, then all the participants may end up all in one place and it's going to be hard to control the crowd. So they assign location and they must go to the correct location. So this is one logic. And the other one is that they can only register once. So if you register in the morning, you cannot come again or an hour later and try to register. So technically, it translates to at least 2 database select one insert. Because why? I got to check location correct now. I got to check if you come before now. Then I got to after that I'm going to create a result registration record. So in terms of database operation, it's over 1,000 database transactions in 1 second. And that's a huge number. And your database, you can only scale vertically. Of course, you can do things like sharding. But if you do sharding, then your application logic has to change. So it's not easy to say that I just shard my database. So the approach is that, the result is that if you take this approach, you're likely going to hit the bottleneck. And what if the following year, as time go by, the number of participants actually increase? So you cannot scale because you at this requirement you already hit your bottleneck. So you cannot even scale further. Even if you can make it work tomorrow when the requirement change, or maybe instead of 1,000 locations it becomes 2,000. So you cannot scale. So we actually propose an event streaming architecture. So how it works is that throughout the entire registration process, from the point that the participant go to the location, register himself, throughout that transaction, there's not a single database operation. We actually pump it into an event streaming platform and we process it on the fly in real time so that the result generated in real time. And you may ask if I use this approach, where my data goes to. So don't worry, so we actually asynchronously capture in the database as the registration happens. But then it doesn't stop the processing, it doesn't so-called couple in the processing pipeline. So the processing is straight through using event stream processing, and then asynchronously capture in the database for your reporting and others. So roughly I'm going to explain how it works. So you have a stream processor running within your stream processing platform. You're using Kafka, by the way. So you have your data actually preloaded into the streaming platform. So you have the participant database, you have the assigned location. I already spun the processor. It's already cached over there. So as your registration events start coming in, so every time the participant actually scans his IC, so a new event will be created here, and it will be processed on the fly by this stream processor over here. So what it does is that it do a real-time processing by matching the location and making sure that the participant is not registered before. So all these are done on the fly, and there's not a single database coupling here as we do this. And then it immediately generate a result stream, and then you get an instant status, whether you are registered successfully or not, or sorry, you come to the wrong location, or all this thing. It's instant, almost instant. And asynchronously, we sync to the database. so that you can still do a regular reporting and of course for your long-term consistency. So this is actually how it actually works. So you can, with this setup, you can achieve very high throughput, very high performance. So instead of just telling you this, I'm going to show you some test results. So this is a stress test that we actually did over 1 hour. The stress test actually go beyond the requirement already. Just now I show you the so-called the 1 million throughput that I show you. This is actually going beyond already. It's more, almost 2 times the throughput requirement. And we are getting sub-second response time with this setup. So you can imagine in 1 hour, we have 1.7 million registration transactions through the event streaming. At the 90 percentile and 95 is actually, even at the 99 percentile, it is still sub-second. So this thing really can fly and really can scale. Yeah. So next, actually, of course, we do microservices and we deploy in containers. So we use our company EGP, the Equal Government Platform, to build this application. And we run on EKS, and ECR is actually a container registry. So this actually helps us, really help us in this project, because we find that when we are doing the performance tuning and all this, we really got to scale the containers, especially the services, the containers, microservices that are involved in the registration. So we really got to, without this container, we cannot just scale the part that we want. So it actually does really help us. So next, we were talking about visibility. So we actually implement observability. So these are some of the charts that we have when we were setting up the system. So we actually monitor all the Kafka, ASQL matrices, so that instead of just knowing the surface, like for example, whether your CPU is high or your memory is high, or whether your storage is full, that kind of thing. Those are basic stuff, we still need them. But on top of that, we actually went down to deep into the internal workings of because at this kind of high concurrency, without this kind of visibility, when something goes wrong, you'll be totally lost, you don't know where to go. And if you go straight into the application log, you find that it's like a waterfall. You cannot, it's too many things already. You cannot, a human cannot possibly look at the logs and expect to know what happened. So we use our own monitoring stack. It's one of our product suite. In case you're interested, we can talk more about it. So it's a suite of services that does monitoring and observability. So it's capable, it's ingesting all kinds of logs from the OS, from the application, and it supports some of the common middlewares like all this Kafka, all this we definitely can be supported. Even some of the databases, you can actually collect all the matrices, and then you can start setting up different charts to have different views of your matrices in a way that makes sense to you, in a way that can quickly help you pinpoint or isolate the issues. I'm not going to talk too much about that because John is going to cover some case studies on how we use all these tools to actually troubleshoot issues. Yeah. So I think I have covered more or less how we actually build this app. It applies some of these principles, design principles. Again, I mean, as what CK mentioned, it's not a requirement spec. It's not a checklist that you go through. It takes every system, every requirement is different. These are just the principles. It doesn't mean that to achieve scalability, I do one. To achieve B, I do two. It's not this way. It's basically more than that. So we have the experience in doing that, and I mean I more or less show you how I actually apply this principle to build a truly high performance and high resilience system. So hopefully, this is hopefully you enjoy what I share, and I hope it's useful to you when you go back and look at your own systems. So I'm going to pass this to the speaker. So John is going to explain to you how we actually manage this infrastructure. in a high performance way. So I think before that, any questions? I can take some questions. There's one question regarding the database. Is it a 3AZ master stage? Okay. So in terms of database, we actually use AWS RDS. So RDS, we use SQL Server, and it is there's multi-AZ setup, and you cross two AZ. But as I said, right, the way it is casted, although it's only 2 nodes, but there's actually, because it's managed by AWS, so it's only available across two different AZ. Yeah. So it's a active passive setup, but there's actually there's actually a witness list that serve as the third node. Yeah. So answer to you is that actually it's across two AZ. So I just read the question out. So a lot has been mentioned on leveraging cloud-native services. So what is the one Aquarius view on the readiness of government agency to adopt such architecture, and how can we overcome adoption challenges? So I would say the government, through the so-called direction from GovTech, is already adopting cloud-native. A lot of our customers actually come back to us and wants to migrate to the cloud. So we are in discussion with them. Some of them we have already helped them migrated. So the adoption is in progress, I would say. And typically, one of the most discussed item when we move to the cloud is that how much are you leveraging on the cloud-native services? So our answer to the agency is that doesn't mean that you use the cloud provider services means automatically. Like we say, it's not a checklist. So if you use all the cloud services, does it automatically make your application cloud-native? We thought the answer is no. So we have to, in the process, we have to re-architect certain part of that. And sometimes it doesn't mean that you need to go cloud-native. For example, you deploy your own Kafka, and then you do an event streaming or event-driven architecture. But that is not provided by the cloud, but it is part of being cloud-native. So there's no one straight answer to say that by having everything using a cloud managed service means you automatically makes your application cloud native. So that is not the way we look at it. Yeah. So the short answer is that yes, the agencies are actually adopting the cloud native. It's just that they have a different idea of what it means to be cloud native. So typically it's a long discussion with them, but in the end, yeah, there's a way to somewhere in the middle and then move on. Yeah. So I think I'm going to pass the next speaker in the interest of time. Otherwise, we're going to have a late lunch.